Good afternoon, student. After a long gap, I am here to prepare a video lecture on a very important subject, and that is Planck's radiation law from Bose-Einstein statistics. And particularly, I am preparing this lecture for you, that means M.Sc second semester chemistry student. And you know that in the last month I have prepared most of the important aspects of the statistical thermodynamics, like Maxwell-Boltzmann statistics, Bose-Einstein statistics, as well as the Fermi-Dirac statistics. Now, in continuation of those lectures, today I am very specific, because you know that when you study the Bose-Einstein statistics or any Maxwell-Boltzmann or Fermi-Dirac statistics, another part is the application of all those statistics. And this Planck's black body variation, or you can call it that how that Bose-Einstein statistics will be useful for the derivation of this very, very well known Planck's radiation law, because it was developed in long back, I think 1900, and Bose derived that equation in 1924. So you can understand the time gap between. So that means it is not an empirical equation, and of course with the help of quantum statistics that can be derived. Now again, I am really grateful to that our Pandit Ravi Shankar Shukla University for providing me this lecture capturing facilities, particularly Professor Balwant Singh Thakur, as well as Dr. Dipti Thakur and Dr. Indra Kumar, and my research scholars Abhishek Kasenja. As usual, that I have referred some of the very important books related to the statistical thermodynamics, but frankly speaking, for deriving this equation, I have referred large number of research papers, and I have also referred the original research paper of Professor S.N. Bose. Now, most of the time, if you see the syllabi, generally sometimes we are interested in the complete derivation of Bose-Einstein equation. Of course, it is for indistinguishable particles, identical particles, and of course we apply it for the photon. But sometimes there is a second part, that after the derivation you have to derive the Planck's radiation. Now you know that we have already celebrated that 100 years of Bose-Einstein statistics, because it was discovered in 1924, and there appear large number of good articles. And for complete derivation, when I have seen this original research paper of S.N. Bose, I found that the derivation, that is a 4-page paper, and derivation is very big. So for the student purpose, I have slightly modified that equation for the student purpose, so that students can very easily understand that Planck's black body radiation, and he can derive that equation from the Bose-Einstein statistics. But I must confess that this is a wonderful research article published in Resonance in February 2025, and most of my derivations and the formula and the notation I have taken from that research paper. Or it is a general article. You know that Resonance is a very important article. Resonance is a very important journal, and the title you can see that derivation of Planck's law of radiation by Satyendranath Bose, and author is Subha Samanta, and she has very nicely discussed some historical concept of that Planck's black body radiation, and then derived that equation on the basis of the original paper. In addition to that, because you are all M.Sc second semester student, and you know that as per the national education policy, we have given more trace on the research oriented things, and you are regularly visiting the library and see the different types of journals and the books. And one of that part I am taking from the literature, and the title is The Journey from Planck's Distribution to Bose Statistics. Because if you really understand the Planck's radiation, it is based on the classical physics, and after this derivation of now, it is a combination of classical and quantum mechanics. So it is a combination of classical and quantum mechanics, and very simple language. I will try to explain these things. Up that way, you can see here. So you know that whenever I start any equation, I just give the general information, because what is our objective? Don't get confused. I have already derived very mathematically the Bose-Einstein, but today I only discuss the Planck's radiation law on the basis of Bose-Einstein statistics. So you must know what is the final formula of the Bose-Einstein statistics, and you know that Ni and statistical weight factor, you know that these things, and this is our final equation. What is important here, that here I am using alpha and beta. You know that beta is equal to 1 by kT. You all know it is a Boltzmann constant, but because we are derive this equation for boson or even photon, so for that mu is equal to actually 0. So therefore my equation is that 1 divided by exponential h mu kT minus 1. So I have to derive Planck's radiation law with that Bose-Einstein equation. Now you know that there are, you might have aware of this, our national quantum mission, and Bose-Einstein statistics have a tremendous application in the chemistry as well as the physics, astrophysics, everywhere. And one of the most important applications, therefore I have written, is number 1A, that is the black body radiation. And also, I will not go into details of the history of that Bose-Einstein statistics and then the Einstein extension development and other things. Bose-Einstein condensation is also very important. Superfluidity, superconductivity, laser physics, cosmology, phonons and solid state physics, quantum statistics. But my concentration is only on the black body radiation, that how objects emit radiation depending on the temperature. And I think during your B.Sc classes, you have gone through that black body radiation, what is actually black body radiation. And I will not solve the original Planck's derivation of that black body radiation, but very simply I will explain this thing. If you see very carefully this photographs, and I have taken this information from a website where they clearly given this Planck's radiation law, the final equation, and in one side SN Bose, another side you see great, this is Max Planck, you all know. He was also a Nobel laureate, he was awarded Nobel Prize in 1918, although he was awarded in 1919 due to his great quantum theory, you all know this. And if you see this final equation of that, so there are three parts. One part is actually we would like to calculate the total energy, how energy is distributed and that in photon and just in the, under the black body. And there is a part which is called phase space volume. In physics, phase space means actually the all possible combination of the position and the momentum. Because if we are talking about the photon and radiation, so therefore we just want to know that the probability of the photon, how it radiates, that is the thing. So this is the final equation, and you are all aware of all these things. 8 pi frequencies where the velocity of the light exponential like that. There is actually Planck's law. So I have to derive from both Einstein statistics to the final equation. So that is called the energy per unit volume per unit frequency. And it describes the electromagnetic radiation. You know that if I just consider a black body, because it absorbs, its ideal condition, it absorbs all types of radiation. And you know that due to thermal, if I just change the temperature, so it also emits radiation. So that it explains how the intensity of the radiation, and there is a graph, you all know that intensity of the radiation and the wavelength. So it explains how the intensity of the radiation varies with the wavelength and the temperature. And it is very, very important law, no doubt about it. It is very important law for the quantum mechanics as well as the radiation physics. So just for a minute, I just want to, there are large number of photographs regarding the black body radiation. It is not like it is just typical, I am talking these things. And it absorbs all types of radiation like that here and here. And if I plot a graph between the radiation intensity and the wavelength, this plot is just symbolic diagram. So if you see that, if you increase the temperature, you know that. If I ask you what, can you give me one example of black body radiation? Yes, you know that when you hit the iron, glowing rays, or even if you can say the filament bulb, this switch, so there is a glow. So these are all types of things. So and it is discovered by Max Planck, black body radiation. So our objective is that we have to consider that this type of cavity of like that, and then there is a photon, large number of photons, large number of photons are there, how it radiates, and of course we have to calculate the different type of standing waves and the mode of standing waves. That is our objective. Actual energy per unit volume with respect to different frequencies like that. So it is one type of, you know, that it also radiates if you change the temperature like that. So our objective is not to study the black body radiation. Our objective is that use of how this thing. So this is the expression of this black body radiation, and you know that it is a classical, when he, now just you think that it was discovered in 1900, and then of course Einstein also studied this black body radiation in 1905. He is also Nobel laureate. And Niels Bohr is also studied this thing in 1923. But Actual is the 1924 is the actual exponent. So it is a very important theory, and you know that it is the first quantum revolution in the 20th century. And then of course Bose tried to determine that equation with the help of the light quantum mechanics and other things. And of course I will not discuss today because if you understand the Planck black body radiation, so sometimes at low frequency radiation we can use the Wien displacement law, and for high frequency we can check that radiation, that is called the Rayleigh-Jeans law. Rayleigh is also a Nobel laureate, you know. But after this derivation using the Bose theory, we can able to explain the complete range of the radiation. So that is the importance of the Bose theories like that. And I am showing you the original research paper of the Max Planck, which is published in 1901. You see, it is of course in the German language, and if you see very carefully, just see this thing. I have used a number of books, research papers, Indian research papers, but just for the sake of simplicity, I am just showing you that this formula 858 frequency is the velocity of light, and if you see this, you see this is like that. You see here. This is original research paper in German language, energy 85, it's exactly same, 1 divided by exponential h nu divided by kBT minus 1. So there are two forms. In terms of frequency, we can write this thing. In terms of wavelength, you know that frequency is equal to c divided by lambda. I will show you. So we can also calculate this thing. So this is the original paper of that Planck, and I am really grateful to the website as well as the Google. Everything is available in the literature nowadays. You can see that later and everything. So now I am start the derivation. So actually when Max Planck started the studies of the black body radiation, the quantum theory of radiation had not yet been developed. So his theory is based on the, he just takes the resonator or the oscillator type, harmonic oscillator. And it is based on the classical mechanics and electromagnetic radiations and other things. And as I have already discussed with you, this is a very, very famous equation, because after the discovery of the Planck equation, many other scientists, and they are also Nobel laureate, like Albert Einstein also modified it, and some proposed some quantum theory, 1905. Another scientist, Niels Bohr, you know, also. So most of this derivation is based on the classical electrodynamics with emerging quantum ideas. So there is no problem, that is also correct. But while studying this quantum statistics, Bose thought that he can derive that equation with the help of quantum statistics. Then he prepared a manuscript and tried to publish it, but somehow it was not published. I am talking in the year of 1924. Then he actually, S.N. Bose was motivated and inspired by this revolutionary work of the Max Planck. And then he thought that I must prepare a manuscript. And when it was not published in a philosophical journal, then he wrote a letter to Albert Einstein regarding this black body radiation and requested him to translate it in German. And fortunately, and that letter is very important. I am not showing you that letter. One letter that S.N. Bose written to Einstein, and Einstein replied. That is available in the literature. You can please go through that letter, and in that letter they have mentioned the actual black body radiation. So ultimately that paper was published in Jet Physics in December 1924, and it is available in the literature. And of course, after that, that English version is also available, and complete derivation is available. And I have used some of that part, not complete part, because there is very some mathematics are also involved. So this is the actual original paper of this university. Title is like that: Planck's law and the light quantum hypothesis. And again, that English translation, the beginning of the quantum statistics, Theimer and Budram, is also published in English language. So that is, you see, Planck's law and the light of quantum hypothesis. And this is a 4-page paper. And as I have shown you the first paper in the resonance by that madam, so that article is based on this original paper. So those who are interested in the complete derivation of this Planck's radiation theory from Bose, Einstein, I suggest you, I advise you, please go through that research paper, which is now English translation is available. You see, this is the complete paper, and I have taken some part. But again, I am preparing this lecture, this video lecture for the M.Sc chemistry student, not for physics students, as a part of the application of that Planck's radiation, application of Bose-Einstein for this. So therefore, I will avoid some of the complicated mathematics, but I will use most of the simple things. So there are 4 pages derivation is also available in the literature. Now I am coming to that point that Bose-Einstein statistics gives a more consistent derivation of the Planck's radiation law. Now there is no doubt about it. Everything is now clear. But before going into detailed derivation, I have to write some of the salient features. And because he has already discussed that photons and quanta, the black body radiation, you can consider just like a cavity of black body radiation. And of course, for mathematical purpose, sometimes we just convert into Cartesian coordinate, into spherical coordinate, just like a box. So that is x direction, y direction, z direction. Momentum is also important. The position is also important. Total energy is important. Volume is also important. So I will discuss all these things. So that is the introduction of that. Now I will come to the. So the photons may have the energies between the 0, 1, to different frequencies, 1, 2, up to infinite, and can be moving in all possible directions, similar to the molecules of a gas, as I have already shown you in the black box, different types of, because it absorbs the radiation. Most all these, 100% absorption. And then under the thermal equilibrium, then it radiates. So it can move anywhere, but we have to calculate the actual position, place, and total volume, energy per unit volume with respect to frequency range, nu plus b, like that. So a chamber containing a black body radiation can be considered as full of photons and thermal equilibrium. You can write like that also, we can consider like that. Then of course, x direction, y direction, z direction, and then resulting that I can calculate all these things like that. So in the case of radiation, it is essential to know the number of quanta. You know, that time quanta is also discovered. E is equal to, you know that E is equal to 8. But if you are talking about the photon or the quanta, there is no mass like that. So that time, that is the quanta, if I want to calculate the energy, the ability to do the work. So that time I can write that E is equal to, if it is momentum and the velocity of the light. If you understand these 2 points, first point is E is equal to h nu, energy of the photon, and for the photon actually. So there is no mass, only thing is that. So that is the thing. Now I will start the derivation. Now again let me confess that there are 2 parts of the derivation. In the first part, I will only discuss that from Bose-Einstein statistics, how we calculate the Planck radiation law. If you are not satisfied, so please refer my second part, of course in the same lecture, regarding the details derivation of this thing. So first derivation is very simple. What is that? First point is that the quantization of the energy and the photon gas. So first consider a closed space cavity filled with electromagnetic radiation, and there is a energy. I just want to calculate the total energy E, and temperature is T. Okay. So in this cavity, the radiation is made up of particle called as photons, and of course, because that time Bose-Einstein already discussed this Bose-Einstein statistics, particles are indistinguishable, and generally they are called the bosons with the integer spin, you know that. And each photon has energy given, as I have already told you. Now you just imagine there is a box or even a cavity, and there is a movement of that photon, and just you consider it just like a box. So that types of the radiation, that is called the standing waves, and there may be different types. You can like that, it can be go there like that. This type is also possible. There is a reflection, a reflector is also there. So there are different types of standing waves, or even I can write like that, even that like that. So I have to calculate that mode of that number of modes of that standing waves per unit volume. We just consider that. So the number of electromagnetic modes per unit volume in the frequency range mu 2 mu plus p. So one method is that you have to calculate the standing modes or the number of electromagnetic modes step by step with the help of that Bose original research paper, or you can directly write the number of modes per unit volume. You can directly write this thing and then derive it. Okay, let us solve this thing. So suppose you don't want to derive, I will explain that how we can calculate the number of modes from the original Bose paper. That is not at all difficult. We have to consider the momentum, we have to consider the volume, because there are a large number of photons. So therefore, I have to replace that summation by the integration. And if I just consider a sphere, I can calculate there is no problem. But if you don't want to calculate that number of modes, and from first you write the derivation of complete Bose-Einstein statistics, and then there is a B part, that how you derive the Planck's blackbody radiation. In that case, you can directly write that number of modes 8 pi u square pq Tc. So a mode means possible standing wave of the electromagnetic radiation inside the cavity. Just again you consider the black body. Right? It's not like a complete black. So you know this is a frequency, small frequency, like that. So I have to calculate this between that frequency, because frequency is different and very small. So the cavity contains possible electromagnetic standing wave modes per unit volume. So our objective is that I have to calculate the energy density per unit volume. So what should I do? I will write first the number of modes multiplied by the energy of the photon, which is not at all difficult. E is equal to h nu, multiplied by number of photons per mode. Very simple. So first I will write the number of modes. I have not derived, directly I can write. Then energy of the photon, h nu, no problem. And then number of photons is supposed with respect to frequency. So very simple. Just if I solve it, so and I have to replace this value in this equation, and this is nothing but the Bose Einstein statistics, you know. So in first equation, in place of this number of photons, I can substitute this value 1 divided by exponential h nu kt minus 1. I can write like that. So in next page, you see. So energy per mode is equal to h nu and n h nu. So I have written here h nu, and this is nothing but the Bose-Einstein statistic. So what I can write? So here you can write. This is again very simple. First is that mode, second is this space, and third is this. So this h, so here is 8 pi, this h is there, here is nu square, frequency nu, so it is nu cube, c cube, and this thing. So I think you are very happy to see the very simple derivation of this thing. So it is very simple derivation. So directly, again I am just repeating this thing, that first I have to write the Bose-Einstein statistics, then I have to calculate the energy density, number of energy per unit volume with respect to frequency. And so there is only 3-line derivation first, but bear in mind here I have used, or I have directly used the value of the mu. Now in the second part, I will discuss this thing. So this is the equation. But as I have told you that in some places, if you just want to change the frequency in terms of wavelength, this is in terms of wavelength. So you have to slightly modify this thing. So let me just solve this thing. So this is the modification, and how I get this equation. Let me just solve it. Now you know that these are equations in terms of frequency. In terms of frequency, what my objective is that I have to change it in terms of wavelength. So I have to replace that. I have to replace that frequency. You know that frequency is equal to c by lambda. And very simple differentiation, that if I write like x is equal, I can write like that, and mu is equal to, again it is very simple, lambda inverse 1. So you know that here is lambda inverse 1, so nx x minus 1. So here is actually, you can write that -1. So lambda square. So I can write like that. Here is minus. So and C first function into lambda square is equal to frequency. You know, d nu by d you can write like that. But here, of course, here there is a minus. So what does it mean? That if frequency is low, wavelength is high, or if it is high, it is low. But here we are calculated the range. Here we are calculated the range. So therefore, a mathematics student, can understand very easily that what I am doing nothing, because if I am taking the magnitude, because it gives the range very small. It never, you know, the magnetic means consider without considering the plus or minus. So I am just taking this a magnitude, because the magnitude. So what I will do in place of this frequency, have to replace the C by lambda, and in place of dV, I will replace the C divided by lambda square. So see here, this is our first equation using the frequency. It is frequency term. And this is, I just in place of frequency, very simple, C by lambda, and in place of dV, C lambda. So you see that 8, no problem, pi. Now you see C cube cancel, C cube cancel. Now here is actually pi 3, and here is also, so pi 5. Here is 2, 3, so it is pi lambda 5, exponential 8. Again in place of nu, P by kT. So this is very simple derivation, and from that method you can understand the first case, derivation of frequency in terms of frequency, and this is the in terms of wavelength. So this is, you have to write up to that. Now the last part, sometimes students are not satisfied that from where I get that values of this energy or that standing waves, modes of the standing waves. For that, if you are interested, I can discuss with you. So up to first part is enough. That means, right, sorry. Yes. But if you are, again, it is for your knowledge. Now, and I have taken this derivation from the original research paper of S.N. Bose, and I have used some of the direct equation, but of course I will explain it, and that from that resonance paper. So therefore I have written the derivation based on the Bose historical research paper published in 2024. Everything is available there. And again our objective is that the determination of the energy. And first, how I determine that mode, standing wave mode. So first you consider the radiation enclosed in a volume where different types of quanta are characterized by their number 0, 1 to infinite. So the total energy of any radiation, any system, it is very simple. Summation of, because there are a large number of quanta photons, the discrete photons. So this n, and you know the values of the energy, H. But, so what is this? it is the number of photons in mode and energy. But as I told you in my initial discussion, I am talking about a photon or the quanta. There is no mass, and we are considering a black body, a cavity type of the thing. So volume is important, and as because there are large number of photons, so therefore we are adding energy from all modes. So just we replace this summation by integration, and that time also I told you that we consider that energy is equal to momentum and this thing. So this is now here it is actually momentum, and this is or energy density we just calculate, and volume. This is volume, and this is energy density with respect to frequency. So now what I will do in physics, there is a term that is called the phase, space, volume. All possible momentum and the position. And so therefore, you know that the most probable distribution will determine the energy density of the radiation. Therefore, we use the statistic, most probable distribution. The quantum of light having a frequency nu has a momentum of magnitude in the direction of the forward motion, and of course there will be reflector. So you can just I told you that there may be x direction, y and z. Corresponding momentum is px square, py square and pz square. Now, how do I get this h square and u square and p square? So you can understand these things. First, energy is h nu, and second case for quanta, energy is equal to potential and velocity of the light. So potential that momentum is equal to h nu divided by c. As because we are just squaring that square the total momentum, so we will get h square, u square and c square. It is clear that momentum is equal to this. But there is a position as well as 6 variables, I can call it. 6 coordinates and the momentum can be understood as points in a 6-dimensional space. So now we are interested in this, that because that black body contains a large number of cells. So that is called the phase space, eating of the phase space. It related to, you see, dx, dy, dz. It is actually now it is volume actually. In first part also I have written them here, right? Again, same thing, nothing, I am not doing nothing. So but in terms of coordinate, dx, dy, dz, px, py, pz. So there are 6 variables. 6 variables. One is coordinate and the momentum. So it is dx, dy, dz is v, and this momentum px, py and pz. There is small changes in this. So we have already seen these things because you know it is like that. So I have written 4 pi h nu c square h nu divided by c, because this is actually momentum can be calculated like that. So here you have seen that 4 pi h cube, because h square and this h, so h cube. From where I get this thing, I will show you the conversion of Cartesian coordinate to the polar coordinate, spherical polar coordinate. So surface area you can know 4 pi square. So 4 pi h, this is h square and this h, so h cube. mu square CQ V dV. Now you can ask me, sir, why you divided whole equation with that HQ? Because the difference between this equation and this equation, only thing is that I have to remove that HQ. And you can also ask me, sir, why you have written in place of 4 pi, it is 8 pi. That means the whole equation is multiplied by 2. What is the reason for that? Because it is the polarization radiation. So there is a reflection, you just go there and rebound here. So in order to account this thing, two possible state of radiation and polarization. So therefore, I have written 8 pi volume divided by V square CQ dV. So that is actually this mode of this thing. So you can solve it. How I calculate this? The volume of the box. Instead of using px, py, we switch the spherical coordinate. Suppose it x, y, z, r, theta, phi, like that. You can calculate the spherical coordinate. And there is a simple thing that it is because we are interested in this now cell, because there is small space cell. So volume of the cell, surface area, and thickness. So surface area, you know that 4 pi, radius is momentum dp, p plus dp, from this momentum to this. So 4 pi, and you know that momentum is equal to h mu and c. So if I differentiate it, it's a constant. Everything is constant. H is constant, P is constant. So this very simple. So therefore 4 pi, and thick in place of thickness, I can write H, C and T. So 4 pi T. As because it is square, so complete. So H mu is square. So therefore I am getting. So now you can understand from where I get this thing. So 4 pi momentum square, and you know the value of the momentum, h nu c, and value of this dv. So by that method, I am taking this information from the original research paper of. I have already given the exam, the information like that. So last part is now. Last part is there. So I can write 4, and y it is multiplied by 2. I have already told you. Number 2, why I just remove this, and if you see the original letter written to that Einstein, in that letter also that great scientist Bose is also mentioned about this thing. So that can be removed because it represents the smallest quantum unit of phase space. So dividing by h nu, it gives the actual number of photons phase. So therefore whatever the volume divided by h. And y is 2, I have already told you that polarization radiation 2. Just like a reflector is also there. It's just imagination. So finally, in original research paper, it is given as the A. So it's the same. As A is the state actually. So the number of 8 pi, again the volume mu square, frequency equal to. So how to calculate the thermodynamic probability? So what is the difference between the first derivation? There is no difference. Here what I have done, on the basis of original research paper, I just want to make it clear, that how one can get this the number of electromagnetic standing wave modes, or you can call it cells, per unit volume in the frequency interval between the. Then you can substitute this value of this your mode, then total energy, then number of photons. You can get these things. And then second part is also very long derivation. But I have just removed all these derivations. For a given frequency domain, the number of possible distribution can be determined. It is essential to know how the quanta plays into vacant cells. So there are so many derivations is there, but finally you can get this information. So this is the final Planck's equation as per the Bose-Einstein statistics. So student, let me again summarize this thing so that you should not get confused. First part is that I have already discussed, which is very important, Bose-Einstein statistics. Okay. Today I have tried to explain the how that Bose-Einstein equation of statistics would be useful to derive a great theory which was discovered in 24 years ago, because it was discovered in 1900 or 190 and Bose derived this equation in 192. So you can understand. In between then Einstein has already done some work, then Niels Bohr is already done some work. In my present discussion, I have divided into two parts. In first part, for the sake of simplicity and for the simple chemistry student, I use a simple derivation. I use direct value of that mode of standing waves. And you can directly use that mode. And in the second part, I have used original Bose research contribution regarding how you determine that mode and other things. So thank you very much. In next part, I will discuss the application of the partition function. And if you have any problem, you can interact with me. Thank you very much. Thank you.